These are the 5.5 part 1 notes, and we're going to start looking at some properties of logarithms. So, first couple properties we want to look at is that the log base a of 1 is equal to 0, and the log base a of a is equal to 1, and this matters for any number. And then along with this property, we also have that a to the log base a of m is equal to m, and the log base a of a to the r is equal to r. Okay, so a lot of properties here, and we can actually just go through and prove these. So as opposed to going into a detailed explanation, the book actually does a pretty good job of giving us some examples for proof. So I'm going to go ahead and give you those examples. But in order to understand that, one thing that I think is, I should not have included this one here. I'll move on, but I'll return to this property in a couple minutes here. All right, so use the properties of logarithms. Show that the log base a of 1 is equal to 0. If I rewrite this as an exponential, I say that a to the 0 is equal to 1. So rewriting that as an exponential, I can see that a to the 0 power is equal to 1. And we've already learned that any number to the 0 power is equal to 1. Again, 1 to the 0 power is 1. 2 to the 0 power is 1. 1,776 to the 0 power is equal to 1. So all those numbers to the 0 power is equal to 1. So it's just saying that a to the 0 is equal to 1. That's what the log base a of 1 means. Saying that the log base a of a is equal to 1, this is saying that a to the first power is equal to a. Again, 2 to the first power is 2. 1 to the first power is 1. 1,776 to the first power is 1,176. So it's just rewriting that. We're taking these things that we've already known as exponentials, things that you've been learning since 6th grade, and we're writing them out as logarithms as opposed to exponential equations. So it's just kind of working backwards from something we already know. All right, so now we're going to use the properties of logarithms here. Now, we already know this from up here. I've got 2 to the log base 2 of pi. And if I look up here, I can see that a to the log base a of a number is equal to that number. So I could just go through and I could say, all right, I've got 2 to the log base 2. Since I've got 2 raised to the power of the same log base, this is just equal to pi. So that would be the answer. But you might be asking, why is that? Why can I just go through and cross that out? Some people aren't satisfied with just the ability to cross that out, and it's good to question it. I'm going to rewrite this. I'm going to say that this is 2 to the log base 2 of pi. And then I'm going to do what I did in earlier notes. I'm going to arbitrarily write this equal to x, which I'm totally allowed to do. I'm performing an operation. It's just like I can say 2 plus 2. I can say 2 plus 2 is equal to x, and then I can say 4 is equal to x. There's nothing that stops me from writing it as 2 plus 2. I can write it as 2 plus 2 and just know that that's 4, but I could also write it as 2 plus 2 is equal to x. I'm saying it's equal to some unknown value. I'm saying 2 to the log base 2 of pi is equal to some unknown value. Well, let me go ahead and rewrite this now as a logarithm. I'm going to write this as the log base 2 of x is equal to the log base 2 of pi. And now that we're here, we can see that I've got the same log base. And we haven't learned this property yet. I'm actually going to show you this property next week. Or not next week, but in the next set of notes, you'll see this property. But what I can say here is that x is equal to pi. I've got the same log base, and it makes sense that if I've got the same log base and I'm saying some unknown value is equal to the log base of that value, well then x has to be equal to that unknown value. Again, I've got the log of 0.2 raised to the 0.2 to the negative 2 power. I can just go through and cross all this out and say that it is equal to the negative square root of 2. Now, why can I do this? How am I able to do this? And let me make sure this is actually written out a little bit clearer. This is actually, when I write this out, I'm writing this out as the log base 0.2 of 0.2 to the negative root 2. So that's how it would be written out clearly, where I can cross those out. And again, it's that same principle of me being able to go through and saying, all right, I know my answer here is going to be the negative square root of 2, but that's because I can write the log base 0.2 of 0.2 to the negative 2, negative root 2, and I can set this equal to x. So then I can say 0.2 to the x power is equal to 0.2 to the negative root 2 power. And we've already learned that when we've got the same base, I've got the same base here of 0.2, so then I can just say that x is equal to the negative square root of 2, and that's how it is. I don't need to do all that work, though. I don't need to arbitrarily set this equal to anything. I could have just seen that I've got the log base of the same thing here, and those just cross out. Just like here, when I have this natural logarithm of e to the kt, my answer here is just going to be kt. This is going to be my final answer. But again, I can set this up, and I can change my natural logarithm to the log base e to the kt, and I can arbitrarily set this equal to x. I can set that log base e of e to the kt and set that arbitrarily equal to x. I can say e to the x is equal to e to the kt, and I can look and say I've got the same base. Those are going to go away. I can just say that x is equal to kt. So I haven't done anything crazy here. I'm actually just doing properties of logarithms. I'm just saving myself time. So if I have a log base of something that I'm then raising to an exponential, my answer is just that exponent. If I've got an exponential and in my exponent is a log base, those just cross out. So it's just a quick property that we have. I've kind of proven that property for you. It's based on some things that we're going to look at next week, but it should start giving you that introduction and start to make some sense. All right, so now we've got two other properties of logarithms, which I kind of put out of order, but we're going to reference them while we're doing them. So the first one I have is the log base a of m times n can be rewritten as the log base a of m plus the log base a of n. Just like I can rewrite the log base a of m over n as the log base a of m minus n. This is very similar to your exponent rules of how your exponents subtract and how they add. When you're multiplying something of the same base, the exponents add. When you're dividing something of the same base, your exponents subtract. This is the same principle being applied as a logarithm. The other property you need to know, I got to scroll back up here, is the power rule, that the log base a of m to the r power is equal to r times the log base a of m. Now, again, a lot of this is not going to make a lot of sense to you if you're just looking at it this way. It's not that straightforward. It's not that clear when we're looking at everything as hypothetical variables. Let's move from hypothetical variables and look at something a little bit more literal and work from there. So first thing we have here is we've got the log base a of x times the square root of x squared plus 1, where x is greater than 0. Don't worry too much about these. This is just the book giving you, okay, here's the domain of this logarithm. This is the only place that x applies. So write this out as a sum of logarithms and then express all powers as factors. Okay, so what this wants us to do is we've got one logarithm. It wants us to break this up into some other logarithms. So what I look at here is I say, all right, this is log base a, and the first thing I have happening is multiplication. I can rewrite this as the log base a of x plus the log base a of the square root of x squared plus 1. That's from the property of log base a of m times n is equal to the log base a of m plus the log base a of n. I'm saying I've got two things inside my logarithm. They're currently being multiplied, so I can break this up into addition of two separate logarithms. I don't have to stop here because it also wants me to express all powers as factors. So what I'm going to do here is I'm going to rewrite this as the log base a of x plus the log base a of x squared plus 1 to the 1/2 power, because we can change a square root into something to the 1/2 power. That's one of the things about square roots. And now I can rewrite this as the log base a of x plus the log base a, this is what I mean by powers as factors. We're going to take that power and move it out front. This is from what I had to scroll up to. This was our second slide where the log base a of something to a power is equal to that power times the log base a of that item. So I can go through and say I've got 1/2 times the log base a of x squared plus 1. And this is where it stops. You might be asking, why can't I break up that log base a of x squared plus 1? That's a sum. We don't have any rules for breaking up sums or polynomials within a logarithm. So once I get that x squared plus 1, I have to leave it there. I can't turn that x squared plus 1 into another log base a of x squared plus the log base a of 1. That's not how that works. It only works with multiplication. Addition, you just leave together as one logarithm. And then I was able to move that 1/2 out front of that logarithm because the square root is the same thing as raising something to the 1/2 power. So that would be my final answer. I cannot simplify this anymore or reverse simplify this, however you want to look at it. You could argue that this is less simple than the original. So working in like reverse simplification here, this is as far as I can reverse simplify it. So this would be my final answer. All right, we've got another couple examples of this. So write the natural logarithm of x squared over x minus 1 cubed, where x is greater than 1. Again, x is greater than 1 is just the domain, as a difference of logarithms, and then express all powers as factors again. So here the first thing that I'm going to do is I'm going to write this out as the natural logarithm of x squared minus the natural logarithm of x minus 1 cubed. Both of these, it was division within one logarithm, so if you looked at it, we could claim that we're taking the natural logarithm of everything here, that x squared over the x minus 1 cubed. And because of that, we can break that up as a difference. So this is the natural logarithm, or the log base a of m over n breaks into the log base a of m minus the log base a of n. Our log base a here is the log base e, which is the natural logarithm. So I've got the natural logarithm of my numerator minus the natural logarithm of my denominator. So now I can rewrite this as the natural logarithm. I can move both my powers in front, and I can express those as factors. So now I can express this as 2 times the natural logarithm of x minus 3 times the natural logarithm of x minus 1. And then I'm going to leave it here because I cannot break up that x minus 1 anymore. It's just that simple. So if I wanted to like reverse simplify this, moving backwards, I can't move backwards anymore. I've expressed all my powers as factors. I've expressed my division as a difference of 2 separate logarithms. So everything here works out for me, and I'm done. All right, last example, I'm breaking these up. We want to write the log base a of the square root of x squared plus 1 over x cubed times x plus 1 to the 4th power as a sum and difference of logarithms, and we still want to express all of our powers as factors. First thing that I'm going to do is I'm just going to start off with one step. I'm going to write the log base a of the square root of x squared plus 1 minus the log base a of x cubed times x plus 1 to the 4th. Now I'm going to write this out as the log base a of the square root of x squared plus 1 minus, and then I'm going to put everything in parentheses here, is the log base a of x cubed plus the log base a of x plus 1 to the 4th power. Now I put all of this in parentheses because the multiplication that's happening, it's all happening in the denominator. It's not happening at all in the numerator. All of my multiplication right now is in the denominator. I've got one term in the denominator. I've got 2 choices. I could leave this entire thing in parentheses, which I'll do for right now. I could then rewrite this as the log base a of x squared plus 1 to the 1/2 power minus, in parentheses, the log base a of x cubed plus the log base a of x plus 1 to the 4th. And then from here, I can move all of my powers as factors. So since I've got log bases all raised to some power, they can all move out front. And I can rewrite this as 1/2 times the log base a of x squared plus 1 minus the log base a, or 3 times the log base a of x plus 4 times the log base a of x plus 1. And then end parentheses there. I will accept this as an answer when you put parentheses around everything. So when I have parentheses around everything here, I will accept this as an answer. I can clearly see that since this is happening in parentheses, I've got all my multiplication happening in my denominator. The other thing that I can do is I can distribute that negative. So this could become 1/2 the log base a of x squared plus 1 minus 3 times the log base a of x minus 4 times the log base a of x plus 1. The fact that I've got a negative going towards both terms lets me know that both of those terms are in the denominator. I'm dividing it still. I've distributed a negative among something that was being multiplied on the inside. That's just an application of the distributive property. Technically speaking, the book has this as the correct answer, but what is above it is also the correct answer as well. I've still clearly defined that 3 log base a of x minus 4 log base a of x plus 1, that means I've got x cubed times x plus 1 to the 4th power in the denominator of this singular logarithm. So either one of those answers is acceptable. I actually kind of advise just keeping your entire denominator in parentheses. It's much easier to make sure that your signs are correct when everything's in parentheses. And in my head, for me personally, to be able to like clearly define, all right, I have got a numerator here, and then I've clearly got a denominator that has 2 terms multiplying within it because I have it expressed in terms of parentheses and I have those grouping symbols there. I personally think that's a stronger way to express the properties of logarithms. However, many mathematicians, the book kind of argues this as well. The book's technical correct answer is when you have that minus 3 log base a of x minus 4 log base a of x plus 1. But I think at the end of the day, that's just splitting hairs. So I will accept either answer. It's your own personal preference. Whatever makes more sense to you as long as you are correct. All right, so we have de-simplified some things. So now we also want to simplify some things. So we went through the process of breaking logarithms up. Now we want to go through the process of taking a broken logarithm and making it 1. I've got log base a of 7 plus 4 to the log base a of 3. First thing that I want to do is I know that multiplying any factor, if I have that coefficient of that logarithm, I can turn it into a power. So I can call this the log base a of 7 plus the log base a of 3 to the 4th power. And then I can actually say that this is the log base a of 7 plus the log base a of 81. I know what 3 to the 4th power is. That's 3 times 3 times 3 times 3, which is 81. So now I can rewrite this as the log base a of 7 times 81. And I know what the log base a of 7 times 81 is. That's 567. So now I have the log base a of 567. So I've worked, so now I'm simplifying this logarithm. I already have it broken up. I go through the process of saying, all right, both of these are log base a. Let me take that factor and turn it into a power. And when I have actual numbers, I can do real math here. I can raise 3 to the 4th power. I can multiply 81 times 7, and I can get those numbers, but it's still just using those properties of logarithms to get there. All right, so now I got 2/3 times the natural logarithm of 8 minus the natural logarithm of 3 to the 4th power minus 8. So let's go through and start breaking this down. First of all, I can call this the natural logarithm of 8 to the 2/3 power because I changed that factor into an exponent. And then I'm subtracting the natural logarithm of 81 minus 8. I know that 3 to the 4th power is 81. The natural logarithm of 8 to the 2/3 power is the same thing as the natural logarithm of the cube root of 8 squared. That's what happens when we do things to the when we have an exponent to a fraction. Your numerator becomes the power we raise the number to. Your denominator becomes the root that we take of the number. So then I have minus the natural logarithm of 73. Now I've got the natural logarithm of the cube root of 64 minus the natural logarithm of 73. And the cube root of 64 is 4. So I've got the natural logarithm of 4 minus the natural logarithm of 73. Since I have subtraction here, I can go ahead and define this as the natural logarithm of 4 divided by 73. And this is where I will leave it. I say that it's being divided out. So these are something that I can actually break down into some numerical answers. I can leave them as fractions. I can leave them as numbers. Theoretically speaking, I could then go ahead and type in the natural logarithm of 4 divided by 73 on my calculator. And just for fun, let's go ahead and do that. So I will type in the natural logarithm of 4 divided by 73 on my calculator, and I will find that this is equal to negative 2.904. If we wanted to, we could go from the very beginning. We could plug that 2/3 natural logarithm of 8 minus the natural logarithm of 3 to the 4th minus 8 into our calculator, and we would see that that's the same as well. All right, and then we got one last example. So now we're working with something a little bit more abstract. We're working with things that are all numbers here. And again, we want to write this as a single logarithm. I see that all of these are log base a. So since they're all log base a, that means I can combine them. If I had a log base b in there, it wouldn't work. I don't have anything to raise as powers right now, which is good. So I'm going to rewrite this as the log base a of 9x plus the log base a of x squared plus 1 minus the log base a of 5. I'm going to rewrite this as the log base a of 9x times x squared plus 1. And this is minus the log base a of 5. I'm going to rewrite this as the log base a of 9x cubed plus 9x minus the log base a of 5. And then I'm finally going to rewrite this as the log base a of 9x cubed plus 9x over 5. I've rewritten this as one singular logarithm. I don't have any factors that are just hanging out. I don't have any random multiplication that's hanging out. I don't have to worry about moving any powers. There were no powers that had to be moved. And I have this as one single logarithm worked from something that was set up as a sum and difference of logarithms now. All right, you guys have a homework assignment. Please reach out with any questions or concerns and have a great night.